In the previous lecture, we went through examples of inference involving some of the variations of the Bayes rule. One case that we did not consider was the case where the unknown random variable and the observation are both continuous. In this lecture, we will focus exclusively on an important model of this kind, and because we consider only one specific setting, we will be able to study it in considerable detail. In the model that we consider, we start with some basic independent normal random variables. Some of them, the theta j, are unknown, to be estimated, and some of them, the wi, represent noise. Our observations xi are linear functions of these basic random variables. In particular, since linear functions of independent normal random variables are normal, the observations are themselves normal as well. This is probably the most commonly used type of model in all of inference and statistics. This is because it is a reasonable approximation in many situations. Also, it has a very clean analytical structure and a very simple solution. For example, it turns out that the posterior distribution of each theta j is itself normal, and that the map and LMS estimates coincide. This is because the peak of a normal occurs at the mean. Furthermore, these estimates are given by some simple linear functions of the observations. We will go over these facts by moving through a sequence of progressively more complex versions. We will start with just one unknown and one observation, and then generalize. And we will illustrate the formulation and the solution through a rather realistic example where we estimate the trajectory of an object from a few noisy measurements. In this lecture sequence, we will do a lot with normal random variables. And for this reason, it is useful to start with a simple observation that will allow us later on to move much faster. Recall that a normal random variable with a certain mean and variance has a PDF of this particular form. What if somebody gives you a PDF of this form and asks you what it corresponds to? You can answer that this is exactly of this form, provided that you make the identification that 3 is equal to mu. So this is a normal PDF with a mean equal to 3, and whose variance can also be found by matching this constant that appears here with the number 8. This constant here is in the denominator, so we have a term 1 over 2 sigma squared. This must be equal to 8, and from this we can infer that the variance of this random variable is equal to 1 over 16. And if you also want to find out the value of this constant c, you check the formula for normal PDFs. The constant c is 1 over the standard deviation, which is 1/4 in our case, the square root of this number, times the square root of 2 pi. Now suppose that somebody gives you a PDF of this form. It's a constant times the negative exponential of a quadratic function in x. We will argue that this PDF is also a normal PDF and identify the parameters of that normal. First, let's start with a certain observation. A PDF must integrate to 1, so it cannot blow up as x goes to infinity, which means that this exponential needs to die out as x goes to infinity, and that will only happen if this coefficient alpha here is positive, so that we have e to the minus something positive and large, which is going to die out. Therefore, we must have alpha being a positive constant, and let us assume from now on that this is the case. What we will do next is we will try to write this PDF in this form. And the trick that we're going to use is the following. We will focus on the term in the exponent, which we rewrite this way. We take out a factor of alpha, and then we will try to make this expression here appear like a square of this kind, like a perfect square. So what is involved is a certain method, a certain trick called completing the square. That is, we write this term here in the form x plus something squared, and then we may need some additional terms. What should that something be? We would like that something be such that when we expand this quadratic, we get this term and that term. Well, we get an x squared, and then there's going to be a cross term. What do we need here so that the cross term is equal to this? What we need is a term equal to beta over 2 alpha. Because in that case, the cross term is going to be 2 times x times beta divided by 2 alpha. The 2 in the beginning and that 2 cancel out, so we're left with x beta over alpha, which is exactly what we got here. However, this quadratic is going to have an additional term, which is going to be the square of this, which is not present here. So to keep the two sides equal, we need to subtract that term. And finally, we have the last term involving gamma. Therefore, the PDF of x is of the form. We have a certain constant from here. Then we have the negative exponential of this term, e to the minus alpha x plus beta over 2 alpha squared. And then there's the negative exponential of the rest, which is going to be a term of the form e to the minus alpha times beta squared over 4 alpha squared plus gamma over alpha. Now, this term here does not involve any x's, so it can be absorbed into the constant c. The dependence on x is only through this term, and now this term looks exactly like what we've got up here, provided that you make the following identifications. Mu has to be equal to what we have here, but here there's a minus sign, here there's no minus sign, and so mu is going to be the negative of what we have up here. It's minus beta over 2 alpha. And as for sigma squared, we match and say that 1 over 2 sigma squared must be equal to the constant that we have up here, which is alpha. And from this we conclude that sigma squared is equal to 1 over 2 alpha. So we have concluded that a PDF of this type is indeed a normal PDF. It has a mean equal to that value and a variance equal to that value. Actually, to figure out what the mean of this PDF is, we do not need to go through this whole exercise. Once we're convinced that this is a normal PDF, then we know that the mean is equal to the peak of the PDF. To find the peak, we want to maximize this over all x's, which is the same as minimizing this quadratic function over all x's. Where is this quadratic function minimized? To find that place, we can look at the exponent, take its derivative, and set it to 0. So setting the derivative of the exponent to 0 gives us the equation 2 alpha x plus beta equal to 0. And from this, we solve for x, and we can tell that the peak of the distribution is going to be when x takes this particular value. This value must also be equal to the mean. So this is a very useful fact to know, and we will use it over and over. Negative exponential of a quadratic function of x is always a normal PDF. As a preparation for more complex and more difficult models, we will start by looking at the simplest model that there is that involves a linear relation and normal random variables. The specifics of the model are as follows. There's an unknown parameter modeled as a random variable, theta, that we wish to estimate. What we have in our hands is theta plus some additive noise w. And this sum is our observation x. The assumptions that we make are that theta and w are normal random variables, and to keep the calculations simple, we assume that they are standard normal random variables. Furthermore, we assume that theta and w are independent of each other. According to the Bayesian program, inference about theta is essentially the calculation of the posterior distribution of theta if I tell you that the observation capital X takes on a specific value little x. To calculate this posterior distribution, we invoke the appropriate form of the Bayes rule. We have the prior of theta, it's a standard normal. Now we need to figure out the conditional distribution of X given theta. What is it? If I tell you that the random variable capital theta takes on a specific value little theta, then in that conditional universe, our observation is going to be that specific value of theta, which is our little theta, plus the noise term capital W. This is the relation that holds in the conditional universe where we are told the value of theta. Now, W is independent of theta. So, even though I have told you the value of theta, the distribution of W does not change. It is still a standard normal. So, X is a standard normal plus a constant theta. What that does is that it changes the mean of the normal distribution, but it will still be a normal random variable. So in this conditional universe, X is going to be a normal random variable with mean equal to theta and with variance equal to the variance of W, which is equal to 1. So now we know what this distribution is, and we can move with the calculation of the posterior. So we have the denominator term, which I'm writing here. And then we have the density of theta. Since it is a standard normal, it takes the form of a constant. We do not really care about the value of that constant. What we care really is the term on the exponent. And then we have the conditional density of x given theta, which is a normal with these parameters, and therefore takes the form c e to the minus 1/2. It's a density in x, and so up here we have x minus the mean of that density, but the mean is equal to theta squared. And this is the final form. Now, what we notice here is that we have a few constant terms, another term that depends on x, and then a quadratic in theta. So we can write all this as some function of x, and then e to the negative of some quadratic in theta. Now, when we're doing inference, we are given the value of x. So let us fix a particular value of little x and concentrate on the dependence on theta. So with x being fixed, this is just a constant, and as a function of theta, it's e to the minus something quadratic in theta, and we recognize that this is a normal PDF. So we conclude that the posterior distribution of theta, given our observation, is normal. Since it is normal, the expected value of this conditional PDF will be the same as the peak of that PDF, and this would be our point estimate of theta. In particular, if we use either the MAP, maximum a posteriori probability, or the least mean squares estimator, which is defined as the conditional expectation of theta given the observation that we have made. So this conditional expectation is just the mean of this posterior distribution. It is also the peak of that posterior distribution. So let us find what the peak is. To find the peak, we focus on the exponent term, which is, ignoring the minus sign, the exponent term is this one. And to find the peak of the distribution, we need to find the place where this exponent term is smallest. To find out when this term is smallest, we take its derivative with respect to theta and set it equal to 0. The derivative of this term is theta. The derivative of this term is theta minus x. We set this to 0, and when we solve this equation, we find 2 theta equal to x. Therefore, theta is equal to x over 2. And so we conclude from here that the peak of the distribution occurs when theta is equal to x over 2, and this is our estimate of theta. So our estimate takes into account that we believe that theta is 0 on the average, but also takes into account the observation that we have made and comes up with a value that's in between our prior mean, which was 0, and the observation, which is little x. So this is what the estimates are. If we want to talk about estimators, which are now random variables, what would they be? The estimator is a random variable that takes this value whenever capital X takes the value of little x. Therefore, it's the random variable which is equal to capital X over 2. This is a relation between random variables. This is a corresponding relation between numbers if you're given a specific value for little x. How special is this example? It turns out that the same structure of the solution shows up even if we assume that theta and w are independent normal random variables, but with some general means and variances. You should be able to verify on your own by repeating the calculations that we just carried out that the posterior distribution of theta will still be normal, and since it is normal, the peak of the distribution is the same as the expected value, so the expected value or least mean squares estimator coincides with the maximum a posteriori probability estimator. And finally, although this formula will not be exactly true, there will be a similar formula for the estimators, namely the estimator will turn out to be a linear function of the measurements. We will see that these conclusions are actually even more general than that. And this is what makes it very appealing to work with normal random variables and linear relations. We are now ready to move on to a model which is quite interesting and quite realistic. This is a model in which we have an unknown parameter modeled as a random variable that we try to estimate. This is the random variable theta, and we have multiple observations of that random variable. Each one of those observations is equal to the unknown random variable plus some additive noise. This is a model that appears quite often in practice. It is often the case that we are trying to estimate a certain quantity, but we can only observe values of that quantity in the presence of noise. And because of the noise, what we want to do is to try to measure it multiple times, and so we have multiple such measurement equations. And then we want to combine all the observations together to come up with a good estimate of that parameter. The assumptions that we will be making are that theta is a normal random variable. It has a certain mean that we denote by x0. The reason for this strange notation will be seen later. And it also has a certain variance. The noise terms are also normal random variables with 0 mean and a certain variance. And finally, we assume that these basic random variables that define our model are all independent. Based on these assumptions, now we would like to estimate theta on the basis of the x's. And as usual, in the Bayesian setting, what we want to do is to calculate the posterior distribution of theta given the x's. The Bayes rule has the usual form for the case of continuous random variables. The only remark that needs to be made is that in this case there are multiple x's, so x up here stands for the vector of the observations that we have obtained, and similarly little x will stand for the vector of the values of these observations. So we need now to start making some progress towards calculating this term here. what is the distribution of the vector of measurements given theta. Before we move to the vector case, let us look at one of the measurements in isolation. This is something that we have already seen. If I tell you the value of the random variable theta, which is what happens in this conditional universe when you condition on the value of theta, then in that universe, the random variable xi is equal to the numerical value that you gave me for theta plus wi. And because wi is independent from the random variable theta, knowing the value of the random variable theta does not change the distribution of wi, it will still have this normal distribution. So xi is a normal of this kind plus a constant, and so xi is a normal random variable with mean equal to the constant that we added and variance equal to the original variance of the random variable wi. And so we can now write down the PDF, the conditional PDF of xi. There's going to be a normalizing constant, and then the usual exponential term, which is going to be xi minus the mean of the distribution, which is theta, and then we divide by the usual variance term. Let us move next to this distribution here. This is a shorthand notation for the joint PDF of the random variables x1 up to xn, conditional on the random variable theta. So it's really a function of multiple variables. And how do we proceed now? Here is the crucial observation. If I tell you the value of the random variable capital theta, as before, then you argue as follows. All these random variables are independent. So if I tell you the value of the random variable theta, this does not change the joint distribution of the wi's. The wi's were independent when we started, so they remain independent in the conditional universe. And since the wi's are independent and the xi's are obtained from the wi's by just adding a constant, this means that the xi's are also independent in this conditional universe. Once I tell you the value of theta, then because the noises are independent, the observations are also independent. But this means that the joint PDF factors as a product of the individual marginal PDFs of the xi's. And these PDFs we have already found. So now we can put everything together to write down a formula for the posterior PDF using the Bayes rule. We have this denominator term, which I will write first, and which term we do not need to evaluate. Then we have the marginal PDF of theta. Now, since theta is normal with these parameters, this is of the form e to the minus theta minus x0 squared over 2 sigma 0 squared. And then we have this joint density of the axis conditioned on theta, which we have already found. It is this product here. It's a product of n terms, one for each observation, and each one of these terms is what we have found earlier, so I'm just substituting this expression up here. Now, once we have obtained the observations, so the value of the random variable capital X, that is the value little x, is fixed. Once it is fixed, then the x's that appear here are constant. So in particular, this term here is a constant. We do not bother with it. And what we have is a constant times an exponential in terms that are quadratic in theta. So we recognize this kind of expression. It has to correspond to a normal distribution. And this is the first conclusion of this exercise. That is, the posterior PDF of the parameter theta, given our observations, this posterior PDF is normal. We have e to a quadratic function in theta, and that quadratic function also involves the specific values of the x's that we have obtained. Let us copy what we have found and rearrange it. Once more, we have a constant, then the exponential of the negative of some quadratic function in theta, and the specific quadratic function that we calculated just before takes this particular form. What is the mean of this normal distribution? The mean is the same as the peak, and to find the peak, the location at which this PDF is largest, what we do is we try to find the place at which this quadratic function is smallest. So what we do is to take the derivative with respect to theta of this quadratic and set it to 0. This gives us a sum of terms. The derivative of the typical term is going to be theta minus xi divided by sigma I squared. And this expression must be equal to 0 if theta is at the peak of the posterior distribution. And so we now rearrange this equation. We split and take first the term involving theta, and gives us a contribution of this kind. And we move the terms involving x's to the other side, and this gives us this expression. And finally, we take this sum here and send it to the denominator of the other side. And this gives us the final form of the solution. The peak of the posterior distribution, which is also the same as the conditional expectation of the posterior distribution. Whenever we have a normal distribution, the expected value is the same as the place where the distribution is largest. Let us now conclude with a few comments and words about how to interpret the result that we found. First, let me emphasize that the same conclusions that we have obtained for the case of a single observation go through in this case as well. The posterior distribution of the unknown parameter is still a normal distribution. Our state of knowledge about theta after we obtain the observations is described by a normal distribution. Because it is a normal distribution, the location of its peak is the same as the expected value, and for this reason the conditional expectation estimate and the maximum a posteriori probability estimates coincide. And finally, the form of the estimates that we get is a linear function in the xi's. And this linearity is a very convenient property to have because it allows further analysis of these ways of obtaining estimates. How do we interpret this formula? What we have here is the following. Each one of the xi's gets multiplied by a certain coefficient, which is 1 over the variance. And in the denominator, we have the sum of all those coefficients. So what we really have here is a weighted average of the xi's. Now keep in mind that those xi's are not all of them of the same kind. One term is x0, which is the prior mean, whereas the remaining xi's are the values of the observations. So there's something interesting happening here. We combine the values of the observations with the value of the prior mean, and in some sense the prior mean is treated as just one more piece of information available to us. And it is treated in a sort of equal way as the other observations. The weights that we have in this weighted average are that each xi gets divided by the corresponding variance. Does this make sense? Well, suppose that sigma I squared is large. This means that the noise term Wi is very large, so xi is very noisy. And so it's not a useful observation to have, and in that case it gets a small weight. So the weights are determined by the variances in a way that is quite sensible. Those observations that will get the most weight will be those observations for which the corresponding noise variance is small. So the solution to this estimation problem that we just went through has many nice properties. First, we stay within the world of normal random variables because even the posterior is normal. We stay within the world of linear functions of normal random variables, and the form of the formula that we have itself has an appealing intuitive content. We now continue our discussion of the model in which we obtain several measurements of an unknown random variable theta in the presence of additive noise under the same assumptions as before. Theta and Wi are all independent random variables and they are also normal. We have seen that in this case the posterior distribution of theta is a normal distribution and takes this particular form. We found the mean of the posterior distribution, which is also the maximum posteriori probability estimate, and it is given by this expression. Now that we have an estimate in our hands, we can ask how good is this estimate? And for this we need an appropriate performance measure. For estimation problems, a reasonable performance measure is to look at the mean value of the squared error. But given that we have already obtained observations, what we're interested in is the conditional mean squared error. This is the error that's remaining after we have seen the observations. Now, let us notice something here. If I tell you the value of the observations, then my estimator is completely determined. The estimator is a random variable that processes the data and comes up with an estimate. So, although it is a random variable, once I tell you the value of the observations, the value of this random variable has been completely determined, and so we can replace it with its actual numerical value, which is theta hat, and it is given by this expression. Now remember also that theta hat, the estimate that we're using, is the mean of the posterior distribution. In this conditional universe where we have conditioned on this information, theta hat is the mean of this random variable, so we're dealing with the square distance from the mean, and then we take the expected value, but that's nothing but the variance of theta in this conditional universe. So what we're looking for is the variance of the posterior distribution of theta given the observations that we have obtained. Can we eyeball the variance by just looking at this formula for the posterior distribution? More or less we can. Recall this earlier fact that if I give you a density of this form, you recognize that it is normal, and you also recognize that the variance is determined by the coefficient that comes next to the term of the form x squared. Now this is a PDF involving a variable x. Here we're talking about a PDF of theta, so what we're looking for is the constant that sits next to the theta squared term. there's going to be multiple theta squared terms, so we need to collect all of them, and so we find that the overall coefficient sitting next to theta squared terms is as follows. From this we obtain a contribution of 1 over 2 sigma 0 squared. And similarly, from here we're going to obtain a coefficient next to theta squared of 1 over 2 sigma 1 squared. We continue the same way. And finally, from the last term, we obtain a contribution of this kind. Now, we take this factor of 2, move it to the other side, so we know what 2 times alpha is, and then we need to take the inverse of that so as to obtain 1 over 2 alpha. And what we obtain is that 1 over 2 alpha, when alpha is given by this expression, is equal to this expression here. And so we have found the conditional variance, the variance of the posterior distribution of theta given the data that we have available in our hands. Now, this is the mean squared error given that you have seen some particular piece of information. What about the overall mean squared error? This is the quantity that you care about before you go and make the actual measurements. This tells you how well you expect to estimate your random variable theta. Well, we can use here the total expectation theorem and write the expected value as a weighted average of the conditional expectations under different scenarios, namely under different measurements of x, and average those conditional expectations over the possible values of x. Now, this quantity here is actually a constant. It is this constant here. So we can pull it outside the expectation. What we're left is the integral of a PDF over all possible values, which has to be equal to 1. So what we're left with is just the value of this constant, which is this particular number. And so we conclude that the overall unconditional mean squared error is also the same. This makes perfect intuitive sense. Our mean squared error is going to take this value no matter what I observe. So on the average, it will also take that particular value. Now, this expression that we have derived is also quite intuitive in its content. Let us try to understand some special cases. Suppose that sum of the variances of the noise terms is very small. If one term is small, this means that the corresponding term here is going to be big. So the sum of those terms is going to be big. As long as one term is big, then the sum is also big, and then 1 over that is going to be small. So in that case, the mean squared error is small. What this is saying is that if just one of the measurements has low noise, then the uncertainty that remains for my random variable that I'm trying to estimate, that uncertainty will be small. I'm going to have a small error. On the other hand, if all of the noise variances are large, then this means that all of these terms here are going to be small. I'm adding small terms. 1 over something small is something big, and so the mean squared error is going to be large. That is, if all my measurements are very noisy, then I do not expect to estimate my random variable particularly well. Let us now look at one more special case. Suppose that all the variances are the same, the noise variances as well as the variance of the prior distribution. In that case, this expression here is going to become 1 over, we have the sum of n plus 1 terms, and each one of those terms is 1 over sigma squared, which is the same as sigma squared over n plus 1. This expression makes quite a lot of sense. It tells us that if we obtain more and more observations, that is, as n increases, we improve our performance. the variance of the posterior distribution, or the mean squared error, goes down in this particular way. Now, perhaps the most interesting aspect of the facts that we have established is this equation here that tells us that no matter what this value of little x is, the conditional variance, the variance of the posterior distribution of theta, is going to be the same. In some sense, it tells us that no particular value of x is more informative or more desirable than any other value. In order to really appreciate what that statement is really saying, it's better to look at a very concrete example. So let us revisit the very first example that we studied, in which case we only have one observation, and where theta and w are standard normal random variables. We did go through that example, and we found that the estimator, the maximum posteriori probability estimator, was 1/2 of the observation. And now we are in a position to also calculate the conditional mean squared error given any particular observation. We apply this formula. In fact, we're dealing with this special case with sigma equal to 1. So we use this expression here, and we see that it is 1/2. So we started with the prior variance for theta, which was 1. And after we obtain the observation, our uncertainty gets reduced and the variance goes down to 1/2. And this is true no matter what little x is. Pictorially, here is what's happening. We start with theta being a standard normal, so it has a distribution of this form centered at 0. This is a plot of the density of theta, the prior density. Suppose that we obtain a measurement, and that measurement happens to be equal to 0. If the measurement is equal to 0, then our estimate will also be equal to 0. The posterior distribution of theta is going to be a normal distribution whose mean is the estimate and whose variance is this quantity that we have calculated, which is 1/2, and therefore it is narrower than the original PDF that we started from. So initially we had a fair amount of uncertainty about theta. After we obtain a measurement of 0, this kind of reinforces our belief that theta is somewhere near 0, and so we obtain a narrower distribution. This is our updated belief about theta. But what if I happen to obtain a measurement that's somewhere out here? In this case, my estimate is going to be 1/2 of what I observed. It's here. And the posterior PDF of theta is going to be a normal PDF that's centered around this point and has the same variance, 1/2. So, in some sense, this particular measurement would be thought of as a quite abnormal one. We're really surprised to obtain an observation which is so far away from 0, because our prior distribution told us that theta is somewhere here. So we have been surprised. But after the surprise, and after we form our estimate of theta, our state of knowledge about theta is that theta is a random variable and it has a distribution that's normal, centered around this point, and whose width is the same no matter what particular observation I happen to get. So even though this particular observation value is unusual, after it is obtained, the remaining uncertainty about theta is the same as if we had obtained any other particular value of x. So this is a very remarkable property that's special to this type of estimation problems involving normal random variables and linear relations. It has a very nice side effect. It means that we can say anything there is to be said about the performance of this maximum posteriori probability estimator by just giving a single number. We can characterize performance only in terms of this number, as opposed to having to tell what this conditional mean squared error is for the different values of x. In this segment, we introduce a model with multiple parameters and multiple observations. It is a model that appears in countless real-world applications. But instead of giving you a general and abstract model, we will talk about a specific context that has all the elements of the general model, but it has the advantage of being concrete, and we can also visualize the results. The model is as follows. Somebody is holding a ball and throws it upwards. This ball is going to follow a certain trajectory. What kind of trajectory is it? According to Newton's laws, we know that it's going to be described by a quadratic function of time. So here is a plot of such a quadratic function, where this is the time axis, and this variable here, x, is the vertical displacement of the ball. The ball initially is at a certain location, at a certain height, theta 0. It is thrown upwards and it starts moving with some initial velocity, theta 1. But because of the gravitational force, it will start eventually going down. So this parameter theta 2, which will actually be negative, reflects the gravitational constant. Suppose now that you do not know these parameters. You do not know exactly where the ball was when it was thrown, you don't know the exact velocity, and perhaps you also live in a strange gravitational environment and you do not know the gravitational constant. And you would like to estimate those quantities based on measurements. If you are to follow the Bayesian inference methodology, what you need to do is to model those variables as random variables and think of the actual realized values as realizations of these random variables. And we also need some prior distributions for these random variables. We should specify the joint PDF of these three random variables. A common assumption here is to assume that the random variables involved are independent of each other, and each one has a certain prior. Where do these priors come from? If, for example, you know where is the person that's throwing the ball, if you know their location within, let's say, a meter or so, you should have a distribution for theta naught that describes your state of knowledge and which has a width or standard deviation of maybe a couple of meters. So the priors are chosen to reflect whatever you know about the possible values of these parameters. Then what is going to happen is that you're going to observe the trajectory at certain points in time. For example, at a certain time t1, you make a measurement, but your measurement is not exact, it is noisy, and you record a certain value. At another time, you make another measurement and you record another value. At another time, you make another measurement and you record another value, and similarly, you get multiple measurements. On the basis of these measurements, you would like to estimate the parameters. Let us write down a model for these measurements. We assume that the measurement is equal to the true position of the ball at the time of the measurement, which is this quantity, plus some noise. And we introduce a model for these noise random variables. We assume that we have a probability distribution for them, and we also assume that they're independent of each other and independent from the thetas. It is quite often that measuring devices, when they try to measure something multiple times, the corresponding noises will be independent, so this is often a realistic assumption. And in addition, the noise in the measuring devices is usually independent from whatever randomness there is that determined the values of the phenomenon that you are trying to measure. So these are pretty common and realistic assumptions. Let us take stock of what we have. We have observations that are determined according to this relation, where Wi are noise terms. Now let us make some more concrete assumptions. We will assume that the random variables, the thetas, are normal random variables, and similarly the w's are normal. As we said before, they're all independent. And to keep the formulas simple, we will assume that the means of those random variables are 0, although the same procedure can be followed if the means are non-zero. We would like to estimate the theta parameters on the basis of the observations. We will use, as usual, the appropriate form of the Bayes rule, which is this one, the Bayes rule for continuous random variables. The only thing to notice is that in this notation here, x is an n-dimensional vector because we have n observations, and theta in this example is a three-dimensional vector because we have three unknown parameters. So wherever you see a theta or an x without a subscript, it should be interpreted as a vector. Now, in order to calculate this posterior distribution, we need to put our hands on the conditional density of x. Actually, it's a joint density because x is a vector, given the value of theta. The arguments are pretty much the same as in our previous examples, and it goes as follows. Suppose that I tell you the value of the parameters, as here. Then we look at this equation. This quantity is now a constant, and we have a constant plus normal noise, so xi is this normal noise whose mean is shifted by this constant. So xi is going to be a normal random variable with a mean of theta 0 plus theta 1 ti plus theta 2 ti squared, and the variance equal to the variance of wi. We know what the normal PDF is, so we can write it down. It's the usual exponential of a quadratic, and in this quadratic we have xi minus the mean of the normal random variable that we're dealing with. Let us now continue and write down a formula for the posterior. We first have this denominator term, which does not involve any thetas, and as in previous examples, does not really concern us. Here we have the joint PDF of the vector of thetas. There's three of them. Because we assumed that the thetas are independent, the joint PDF factors as a product of individual PDFs. And then we have here the joint PDF of x conditioned on theta. Now, with the same argument as in our previous discussion of the case of multiple observations, once I tell you the values of theta, then the xi's are just functions of the noises. The noises are independent, so the xi's are also independent. So in the conditional universe, where the value of theta is known, the xi's are independent, and therefore the joint PDF of the xi's is equal to the product of the marginal PDFs of each one of the xi's. But this marginal PDF in the conditional universe of the xi's is something that we have already calculated, and so we know what each one of these densities is. We can write them down, and we obtain an expression of this form. We have a normalizing constant in the beginning. We have here a term that comes from the prior for theta naught, a prior from theta 1. Here is a typical term that comes from the density of xi, which is this term up here. So here is what we have so far. How should we now estimate theta if we wish to derive a point estimate? A natural process is to look for the maximum posteriori probability estimate, which will maximize this expression over theta, find a set of theta parameters, it's a three-dimensional vector, for which this quantity is largest. Equivalently, we can look at the exponent, get rid of the minus signs, and minimize the quadratic function that we obtain here. How does one minimize a quadratic function? We take the derivatives with respect to each one of the parameters and set the derivative to 0. we will get this way 3 equations and 3 unknowns. And because it's a quadratic function of theta, these derivatives will be linear functions of theta, so these equations that we're dealing with will be linear equations. So it's a system of 3 linear equations which we can solve numerically, and this is what is usually done in practice. And this is exactly what it takes to calculate the maximum a posteriori probability estimate in this particular example that we have discussed. It turns out, as we will discuss later, that there are many interesting properties for this estimate and which are quite general. The trajectory estimation problem that we considered gives you a first glimpse into a large field that deals with linear normal models. In this segment, I will just give you a preview of what happens in that field, although we will not attempt to prove or justify anything. What happens in this field is that we're dealing with models where there are some underlying independent normal random variables, and then the random variables of interest, the unknown parameters, and the observations can all be expressed as linear functions of these independent normals. Since linear functions of independent normals are normal, in particular this means that the theta j and the xi are all normal random variables. Carrying out inference within this class of models goes under the name of linear regression. One can proceed using pretty much the same steps as we had in the trajectory estimation problem and write down formulas for the posterior, and it turns out that in every case the posterior of the parameter vector takes a form which is the exponential of and the negative of a quadratic function of the parameters. And this means in particular that in order to find the map estimate of the vector theta, what we need to do is to just minimize this quadratic function with respect to theta. And minimizing a quadratic function is done by taking derivatives and setting them to 0, which leads us to a system of linear equations, exactly as in the trajectory inference problem. And this means that numerically it is very simple to come up with a map estimate. There's an interesting fact that comes out of the algebra involved, namely that the map estimate of each one of the parameters turns out to also be a linear function of the observations. We saw this property in the estimators that we derived for simpler cases. In this lecture sequence, it turns out that this property is still true, and this is an appealing and desirable property because it means that these estimators can be applied very efficiently in practice without having to do any complicated calculations. Finally, there's a number of important facts, some of which we have seen in our examples, which are true in very big generality. One fact is that the maximum a posteriori probability estimate of some parameter turns out to be the same as the conditional expectation of that parameter. Furthermore, if you look at this joint density of all the theta parameters, and from it you find the marginal density of the theta parameters, always within this conditional universe, it turns out that this marginal posterior PDF is itself normal. Since it is normal, its mean, which is this quantity, it's going to be equal to its peak, and therefore it is equal also to the map estimate that would be derived from this marginal PDF. So what do we have here? There are two ways of coming up with map estimates. One way is to find the peak of the joint PDF and then read out the different components of theta. Another way of coming up with map estimates is to find for each parameter the marginal PDF and look at the peak of this marginal PDF. It turns out that for this model, These two approaches are going to give you the same answer. Whether you work with a marginal or with a joint, you get the same map estimates. And this is a reassuring property to have. Finally, as in the examples that we have worked in more detail, it turns out that the mean squared error conditioned on a particular observation is the same no matter what the value of that observation was. And furthermore, there are fairly simple and easily computable formulas that one can apply in order to find what this mean squared error is. So to summarize, this class of models that involve linear relations and normal random variables have a rich set of important and elegant properties. This is one of the reasons why these models are used very much in practice, and they're probably the most widely used class of statistical models. Let us now come back to the trajectory estimation problem that we introduced earlier. We have an object that moves vertically. At any given time t, the height at which the object is found is equal to this expression. It corresponds to the following. The object starts at time 0 at some initial height theta 0. It has an initial velocity of theta 1, but also has a certain acceleration. And if theta 2 is negative, this will be a downwards acceleration, which means that the object eventually will turn and start going down. So this is a typical trajectory of such an object, where here we're plotting the height as a function of time. However, the thetas are unknown and they're random. We do not know what they are. So this blue curve is just a simulation where we drew values for those random variables at random. But if we were to simulate again, we might obtain a somewhat different blue curve because the values of the thetas might have been different. We do not observe the true trajectory directly. What we do observe is certain data points. What are they? At certain times ti, we make a measurement of the height of the object, except that this measurement is corrupted by some additive noise. This is the model that we introduced earlier. And our assumptions were that all the random variables involved, the thetas and the w's, were normal with zero mean and were also independent. In that case, we saw that maximizing the posterior distribution of the thetas after taking logarithms amounted to minimizing this quadratic function of the thetas. So, once we have some data available in our hands, we look at this expression as a function of the thetas and find the thetas that are as good as possible in terms of this criterion. And this is the map methodology for this particular example. Now, for the purposes of this illustration, actually we will change our assumptions a little bit. They will be as follows. Regarding the acceleration, we will take it to be a constant. The acceleration term often has to do with gravitational effects, which are known, so we will treat theta 2 as a constant, and that means that there is no point in having a prior distribution for theta 2. So this term here, which originated from the prior distribution of theta 2, is going to disappear. We will take the variances of these basic random variables to be the same, and because of these constants here will all be the same. Therefore, we can take them outside this expression and outside the minimization. They will not matter, so we can remove them from the picture. The factor of 1/2 can also be removed similarly, does not affect the minimization. Finally, just in order to get a nicer illustration, instead of taking zero means, we're assuming that the initial position has a mean of 200. So we're starting somewhere around here. And furthermore, the initial velocity has a mean of 50, so we expect the object to start moving upwards. How does this change the formulation? Well, remember that this term and this term originated from the priors for theta naught and theta 1. If we now change the means, the priors will change, And what happens, if you recall the formula for the normal PDF and how the mean enters, after you take logarithms, you see that instead of having here theta naught, you should have theta naught minus the mean of theta naught squared. And this leads us to the following formulation. So this is the formulation that we will consider. We obtain these data points, and for these particular data points and for known times at which the measurements were taken, we put these numbers into this minimization, carried it out numerically, and this is what we got. We got estimates for the different parameters, and using these estimates, we can use this expression to construct an estimated trajectory, and the estimated trajectory is given by the red curve. It seems to be doing somewhat of a reasonable job, but not quite. The distance between these two curves is quite substantial. How could we do a little better? Why is it that we're not doing very well? Let's think intuitively. One of the parameters we wish to estimate is theta 1, and theta 1 is a velocity. Now, all of our measurements are concentrated at pretty much the same time. But if you measure an object only at a certain time, it is very difficult to estimate its velocity. A much better idea would be to try to measure the position of the object at different times and use that information to estimate velocity. So let us instead of taking all the measurements around the initial time, have 5 measurements in the beginning and 5 measurements towards the end. The total number of measurements in this example is the same as in the previous example. Once more, we generate a simulated trajectory according to the probability distributions that we are assuming. Then we generate data according to this model, and we wish to estimate this trajectory. We take the data, plug them into this minimization carried out numerically, and this is what we obtain. So we see that here we are doing a lot better. The estimated trajectory is quite close to the unknown blue trajectory, even though the data seems to be scattered quite a bit. This is a very nice property, but is it just an accident of this numerical experiment? Or also, to put it differently, once you get your estimated trajectory, yes, it is true that it is close to the blue trajectory, but you do not necessarily know that fact. It is one thing to have an estimate that is close to the true value, and it's a different thing to have an estimate that you know that it is close to the true value. So how could we get some guarantees that indeed this is the case, that we have good estimates? Here is how it goes. As we discussed before, the posterior distribution of the thetas given the data is normal. And for similar reasons, the posterior distribution of this quantity, which is the true position, it's what we denoted by x of t, the posterior distribution of x of t is also normal. And in fact, what we obtain from this diagram is at any given point, it's the maximum a posteriori probability estimate of the position x of t at that time. However, besides just this point estimate, we have additional information. We know that the posterior distribution of x of t is normal, and so, for example, at this time, this is the peak of the posterior. This is the maximum a posteriori probability estimate. But we are also able to calculate the variance of this posterior distribution. This is a calculation that's a bit complicated for the multivariate case, for the case where you have multiple unknown parameters. We will not get into it, but we did see earlier an example where we had a single unknown parameter and in which we were able to calculate the variance of the posterior distribution. So the idea is somewhat similar. So not only we have an estimate for the position of the object at this particular time, but we also have a probability distribution for what the true position might be. And once we have such a posterior probability distribution, we can find an interval with the property that 95% of the probability is inside that interval. In other words, we construct an interval with the property that the probability that x of t belongs to the interval. Now we're talking about posterior probabilities, so it is a posterior probability given the data. This probability is, let's say, 0.95. Such an interval gives us useful information. Besides a point estimate, it also gives us a range of possible values, and outside this range, it is quite unlikely to have the true trajectory be out there. So here we're showing some confidence intervals that apply to different times, and they're pretty narrow, they're pretty small, and they give us confidence that we have pretty accurate estimates of the true trajectory. These kind of confidence intervals that we have discussed in the context of this example are called Bayesian confidence intervals. And they're very useful when you report your results to not just give point estimates, but to also provide confidence intervals. Coming back to the bigger picture, what happened in this particular example is quite indicative of many real-world applications. One starts with a linear model in which we have a linear relation between the variables that are unknown and the observations, but where also the observations are corrupted by noise. One makes certain normality and independence assumptions, and as long as the modeling has been done carefully and the assumptions are justified, then by carrying out this procedure, one usually obtains estimates that are very helpful and very informative.